probably have a microphone.
No, I'm just going to belt. I can prepare.
This way it gets recorded.
Fair enough.
That's
all right.
15.
I was just about to steal your job.
It's okay. You're welcome to it if you like. Appreciate the backup plans. Yes. Yeah.
Yes.
The air. Okay. Should I wait another minute or should
No,
that's good. It's on. How do I turn this on?
It's on.
Oh, it's on.
It's
Okay, hello everyone. Welcome to the first JILA Colloquium of 2023. It's my great pleasure today to introduce Andrew Hamilton, today's speaker. Andrew Hamilton got his PhD in 1984 at the University of Virginia and arrived at CU in 1986 and has been part of CU and JILA ever since. Today he's a professor in the physics and APS departments and a JILA fellow, and he has previously served as chair of both APS and JILA. So Andrew's early research work focused on supernova remnants, X-ray studies of supernova remnants, as well as a lot of work on cosmology and how we can learn about the properties of the universe from the distribution of galaxies that we observe on the sky. But then, sometime in the early 2000s or so, Andrew was swallowed whole by a black hole, and as I understand, he's been inside of one ever since. He's done pioneering studies of visualizations of what that looks like when you fall into a black hole, developed a wonderful pedagogical model of black hole spacetimes, the river model, and has done excellent work on the interior structure of astrophysically relevant black hole properties. But my impression, presumably, is that Andrew decided that this line of work was too accessible to observation and experiment. And so recently has switched to studying the theory of everything. And he'll tell us about that today. So welcome all, and have at it, Andrew.
Thank you, Jason. I hope you can hear me at the back. Good. I want to spend first a minute introducing Chris Fuchs, who joined us last week as a visiting fellow. I understand he's our only visiting fellow at the moment. He's going to be here for the next 4 weeks, and he will be giving the next JILA Colloquium in February. And thank you, Anna Maria, for stepping down so that we could have Chris. We'll have Anna Maria later in the semester. Chris does amazing stuff on quantum information theory and quantum gravity and all kinds of weird stuff like that, or kind of. And you should talk to him. He's got an office next door to Adam on the 4th floor in the X-Wing. He's with us. Let's have a hand for Chris. So as Jason has explained, I am certifiably crazy for 2 evident reasons. The first is that I indeed work on what happens inside astronomical black holes. One of the very few people in the world who does that. How could you possibly do that? Everybody knows you can't see inside a black hole. But sometimes what everybody knows isn't actually the truth. The inside of a black hole is the other place besides the Big Bang. It has got the most interesting physics on the planet. It deserves to be looked at. The second reason I am certifiably crazy is I'm going to give you a colloquium on a theory of everything. Yes? So definitely I am a crank. And I will show you the referee's reports to prove it. So I'm an astrophysicist. What the heck am I doing thinking about theories of everything? I don't actually try to think about theories of everything, but when you work on what happens inside black holes, they kind of come up and hit you over the head. So I didn't find them, they found me. If you're an astrophysicist, your modus operandum is you look at the world around or at the heavens above and say, what do I see? And if I look at you, what I see is spinors, spin-half particles. All matter, leptons and quarks, the stuff that you are made of, is made of spin-half particles. And then there's other things called bosons, forces. All the forces of nature, there are 4 of them, arise from symmetries of spinors. This is the truth, including the 3 forces of the Standard Model, which is a direct product of a hypercharged group, a weak group, and a color group. And then the space-time group is a combination of Lorentz transformations and gravity. All of those are symmetries, and they are symmetries of spinors. And by the way, the spinor is the smallest spin that you can possibly have. It's spin half, and you can't get smaller than spin half. Thank you, Thomas, for, you can see this. Make sure that this is visible online. Thanks, Thomas and Wild, for making this for me. It's called the Dirac belt trick, and let me show you how it works. I rotate this half a turn, then that's a full turn, and it's all twisted up. And then I rotate it another half turn and another half turn, and lo and behold, 720 degrees, it gets back to where it was, which is just like a spinor. Do you want me to do that again? Yes. Or did you already get it? Physicists love this kind of stuff, don't they? See what happens. Half a turn, 1 full turn. Then another half turn and another full turn. Did I cheat? Yes. What is a spinor? If you went to grad school, and some of you did, you learned about spinors. Back in high school, you learned about vectors. You learned something very interesting, courtesy of René Descartes in 1637, who pointed out, oh, there's things called Cartesian axes. There's an x1 and a y1 and a z1. And if you're interested in vectors, if you're interested in geometry, you can express any vector as a linear combination of the x, y, and z things. And it was a revolution because it turned geometry into algebra. When I learned this in high school, I was so happy because I had a thick book on geometry and it went straight in the bin. Thereafter, it was all algebra. Were you taught about spinors in high school? Sadly, no. Yes, you should be taught about those things. Were you taught about them in quantum field theory? I'm guessing no, and you should have been. Are you listening, all of those of you who teach quantum field theory? This is how you should teach it. It's like high school stuff. A spinor in n space-time dimensions is indexed by a bit code, not by a single letter x, y, z, but by a bit code. And that bit code has n over 2 bits, half the number of space-time dimensions. Where does that factor 2 come from? It becomes because spinors intrinsically have a complex structure. And that's good because quantum mechanics comes equipped with a complex thing called I, which is absolutely central to all of quantum mechanics. Where does it come from? Well, spinors require it. I don't know who said that they do, but that's what it has to be. So a spinor is a linear combination of something which has n over 2 bits. I'll show you what that looked like. If you're a mathematician, a mathematical physicist, you would know that mathematically, vectors and spinors are representations of the group spin n of rotations in n space-time dimensions. Physicists commonly call this SON. I call it spin n because that is the covering group of SON, And it is the actual group which acts on spinors, because, hey, spinors are spin half and not spin 1. SO1 acts on vectors. Covering group of that is spin n. And the vector representation has dimension n. The spinor representation has dimension 2 to the n over 2. So let me show you the simplest possible example. You're all familiar with this. Thank you, Thomas and Wilde, again for doing this, driving all the way down on Tuesday to make this happen. This is the simplest kind of spinor. It's a Pauli spinor in 2 or 3 dimensions. It's got one bit, and that bit can be either up or it can be down. There's 2 complex components. It can be a linear combination, complex linear combination of up and down. Isn't that simple? If it's 2 dimensions, what you have is a rotation about the axis. Let me go back and show you a little bit what it's got in this graph on the right-hand side. Have I got a pointer somewhere? That's okay. I'll use my thing. If you look here, I've divided the axes into pairs. If you're dealing with spinors, n space-time dimensions, you pair up the axes. Why? Because you've got the complex structure. And they turn out to act mathematically as if they were complex axes. So there's a real axis and an imaginary axis, and they combine to produce a complex axis. And then a rotation in those 2 axes produces a phase rotation of the Pauli spinor. But in reality, we live in 4 dimensions, 3 space and 1 time dimension. And that's where the real world lives. This was introduced by Dirac in 1928. A Dirac spinor has 2 bits consisting of a boost bit and a spin bit. And each bit can be either make this for the camera. Each bit can be either up or down, up or down. Altogether, there's 4 complex components. This is what an electron looks like. An electron is a Dirac spinor. It's got these 4 complex components, and those 4 complex components encode the structure of space-time. 4 complex components means 8 real components, so 8 degrees of freedom, of which 6 account for Lorentz transformations and 2 account for amplitudes of particles and antiparticles. So a Dirac spinor has the relativistic structure of space-time built into it. If you ask, where does the Lorentz structure of space-time come from? It's built into the fundamental particles of nature, spinors. One other thing, I said there were 4 components, and indeed a real massive spinor is a linear combination of all those 4 components. If the spin and the boost bit are aligned, the boost bit basically says which way you're moving in space, which direction, what's the direction of your momentum, and the spin is saying which way you're pointing in space. So the momentum and the spin, they don't have to be in the same direction. A real electron is massive, and it's a linear combination of boost bit up and boost bit down. It has a definite spin, but it's a linear combination, and that's what makes it massive. But natively, spinors are massless, and in that case, they either come in right-handed or left-handed varieties. It's called chirality, right-handed or left-handed. It's a big deal because the weak force only affects the left-handed spinors, so we know it's important. Back in the 1970s, there was a lot of excitement because Steven Weinberg had predicted in 1967 the form of electroweak symmetry breaking, and the predictions of that model, which included a W boson and a Z boson and their masses, was confirmed during the late 1960s and early 1970s. And by the mid-1975, there was a frantic effort of, wow, perhaps we can unify not just the weak force, but all the forces, all the standard model of physics, including the weak and the color force. And the grandest of those grand unified theories was spin 10, the group of rotations in 10, not space-time dimensions, but 10 internal dimensions, independently proposed by George and Fritz and Minkowski in 1975. Spin 10 contains the three forces of the standard model of physics in a very elegant fashion, and I mean that in a mathematical sense. So spin 10 has 5 bits, and therefore 2 to the 5, 32 spinors. There's 2 weak bits, I call them the Y bit and the Z bit. If you want to know where that comes from, they're named after the LSST astrophysics bands. Y and Z are infrared bands. And then there's quarks coming in. There's a red color, and then there's a green color, and then there's a blue color. Like that. This was first pointed out, this spin thing, whoops. The fact that you can characterize the standard model with 5 bits was first pointed out by Frank Wilczek in 1998. And he should have noticed back in 1998 what I'm going to tell you. I don't know why he didn't. But for example, 5 bits, the all-bit up spinner is the right-handed neutrino. If I flip the Y bit, it turns it into its left-handed partner. If I then flip the Z bit, I've turned it into the right-handed electron. If I flip the Y bit back again, I've turned it into the left-handed electron. And if I want to make quarks, instead of having all color bits up, I flip 2 of them, and now I've got 1 red quark pointing upwards, and it's a left-handed red quark. Or I could have a green quark by making the green one, or the blue one up. And if I flip the Y bit once again, that flips the chirality from right to left-handed. And if I flip the Z bit, it flips it from an up quark to a down quark. This may look like kindergarten stuff, but I assure you, this is the real mathematics of it. You don't have to believe me. You can look at Wilczek's article. So I started looking at this 4 years ago, maybe 5 years ago, trying to understand grand unified theories so that I could use them inside black holes or something like that. And one of the first things I did was write up this table, which there's a beautiful review article in 2011 by Bayes and Huerta that write this down, and I wrote this down, and I noticed some really interesting patterns. Now, this is the 32 fermions of a generation in spin 10, and I've arranged it by the number of up bits. So 5 up bits, I'll remind you, 5 up bits, that's a right-handed neutrino. There it is, whoops, it comes in a singlet. Then there's 4 up bits, 3 up bits, 2 up bits, 1 up bit, and 0 up bits. And if you stare at this for a while, you notice something very interesting, or at least I found it very fascinating. The LR is the direct chirality. And what you notice is that the spin 10 chirality agrees with the direct chirality. Right-handed neutrino has got 5 bits up. That's odd number of bits. Left-handed neutrino, even number of bits up. Direct chirality is left. You can see all these columns. They match. So that tells you, so what is chirality? In the Clifford algebra, if you think, if you're familiar with Dirac gamma matrices, these gammas are those Dirac gamma matrices. You take a product of all the vectors in the algebra, you get essentially what is the volume element, which is four-dimensional in space-time, and 10-dimensional in spin 10, and they agree. So it looks like the algebras agree, at least in some one respect. The Dirac pseudoscalar and the spin 10 pseudoscalar are the same. And they have no right to be the same. Is this a coincidence? Well, it's an extraordinary coincidence that happens to be the case. What it suggested to me was that the Dirac and spin 10 algebras are related and not distinct, as is commonly assumed. What is commonly assumed is that you have a grand unified theory of three forces, and then space-time along with general relativity. The two algebras are distinct, and they combine as a direct product. This doesn't look as though it's combining as a direct product. There's a few other interesting things I noticed about this chart of fermions, which is that standard model transformations preserve the number of up-bits. For example, let me take a quark. There's a quark, and it seems to me like it's an up quark. When a gluon comes along, what happens, the gluon has a charge of 1 red and -1 green, and it flips the spinner like that. And you notice it preserves, those gluons preserve the number of up-bits. That is true across the board. The subgroup of spin n that preserves the number of up-bits is SUn over 2. Every SU group that you meet in physics actually arises in this fashion as a subgroup of a spin group, that subgroup that preserves the number of up-bits. So these columns are SU5 multiplets. There's a 1, there's a 5, there's a 10, and there's a 10. Standard model transformations transform vertically. And you notice electrons, they fill out the horizontal thing. So it looks like standard model goes vertical, and Lorentz transformations, space-time transformations, goes horizontal. Once again, it looks as though this knows about not only the standard model, but also about space-time. SU5 was one of the grand unified theories. Standard model is a subgroup of SU5. That's why the SU5, that's why these things are standard model transformations, they go vertically. The final thing I've already mentioned, which is that if you flip the y bit, you flip between positive and negative, you plus half and minus half, you flip the chirality. And electroweak symmetry breaking is simply a loss of y symmetry. Fermions, like electrons, acquire their mass by being a linear combination of y up and y down. So this is very beautiful. Electroweak symmetry breaking is a loss of y symmetry. Normally you would say electroweak symmetry breaking is U1 y cross SU2 left-handed goes to the U1 of the charge symmetry. Which is simpler, losing a y bit? I'm going to say Y unification is obvious. Yes, this should be taught at high school. I hope so, one of these days. So, each of the 2 to the 5th, 32 fermions of spin 10 is actually a Weil spinner. That is a massless chiral Dirac spinner. Each of these things represents a two-component thing. I'll go back. Maybe I can't go back. Never mind. There's 2 degrees of freedom. So you could ask the question, that instead of 32 fermions, there's actually 64 here. 64 complex degrees of freedom. Do the math. What spinor representation has a dimension 64? Answer, 12 dimensions, 6 bits. Yes? It's obvious. So you have to add another bit. And I call it the t bit, or the time bit, because one of those two extra dimensions has to be the time dimension. So I've got the time bit, t bit. I've painted it gold because it's the most important. And then superimposed on those, I've got the y bit, and the z bit, and the red quarky bit, and a green other quarky bit, and finally a blue thing. 6 bits. Theory of everything. Yes? It has to be that way. But it's not so easy. The problem is that chart that I just showed you, I've gone back a slide here, that spin 10 chart cannot possibly be right as it stands. It's a chart written in spin 10, and you notice that each entry is a while spinner, labeled either right-handed or left-handed. And that one while spinner in each little box, each little entry, encodes the entire structure of space-time. How could that possibly be? It cannot possibly be like that. What needs to happen is that it still has to be the case that there are 2 degrees of freedom in each little entry, and those 2 degrees of freedom have to differ by the t bit, because that's the extra bit. But that t bit cannot be the thing that is transforming from between the 2 components of the while spinner. So it's not completely trivial. There's the box. You can see the Christmas puzzle has now been put together. So what happens? You can notice in this spin 11.1 chart, I've got the right-handed neutrino still there, but now its right-handed partner, bit flip partner, is over in where the left-handed antineutrino used to be, and flipping the time bit has flipped the right-handed neutrino to the left-handed antineutrino. So in other words, this is a right-handed neutrino. If I rotate it spatially, this is still a right-handed neutrino. And if I want to make a left-handed antineutrino, I flip the t bit. This works across the board. It's not trivial to see what you do to the algebra in order to make that happen. You know it has to happen, so you spend a long time and you figure out what happens here. Now you may remember telling you that with spinners you have to split the dimensions into pairs, and there's a plus pair, which is the real part of a complex vector, and then there's a minus part, which is the imaginary part of that complex vector. And the trick that you have to do to modify the spin 10 chart to turn it into this spin 11.1 consistent chart is essentially to replace the imaginary vector, replace the I in it, the quantum mechanical I, with this IRGB. That's the color pseudoscalar, a 6-dimensional thing. It's actually amazing that that trick actually works. And to be honest, this whole business of figuring out how this puzzle works has been, are you serious that works? Really that works? So as it says here, number 2, the trick puts the 2 chiral components of each fermion in all bit-flipped entries of spin 11.1 instead of the same entry in spin 10. Each entry still has 2 components, but with the upper t-bit up and the lower t-bit down. And fermions and antifermions are related by flipping the t-bit. You have to do some work. There's some heavy math involved in checking that this actually all works. But the claim was that the Dirac and spin 10 algebras combine in a non-trivial way in the spin 11.1 algebra. So I have to tell you what the relationship between the Dirac vectors, 0, 1, 2, and 3, and the spin 11-1 vectors are. And you notice that the time vector, traditionally gamma 0, is a vector, but the other three, the spatial vectors, are pentavectors. They are 5-dimensional objects. Sounds kind of stringy? Yeah, maybe. This, what does it say? The inner products and Lie algebra of the above space-time vectors are precisely those of the Dirac algebra. And then the Dirac and standard model algebras are mutually commuting subalgebras of the spin 11-1 geometric algebra, consistent with the Coleman-Mandula no-go theorem. I'm going to tell you more about the Coleman-Mandula theorem in just a moment. But there's a no-go theorem that says you can't do this. And I suspect that's one of the way it wasn't done. You have to ignore sometimes. It's consistent with the theory. And another thing, you have to check that all the discrete transformations work. For example, the spinometric, the Dirac spinometric is antisymmetric, and the conjugation operator is symmetric. You do it twice, you get back to the same thing. And the spin 11-1 algebra has those same symmetries. Why? Actually, because 11 is 8 more than 3, and there's a Cartan bot period 8 periodicity of geometric algebras which prove that is true. So yay, the four forces of nature unify in the spin 11-1 geometric algebra, and now you can all go home. We're a little bit early still. What did the referee think of this? Dear Dr. Hamilton, we regret that in view of these comments, we cannot accept the paper for publication in the Physical Review. Let's look at what the referee writes. I've been going through this manuscript again and again, and I finally came to the conclusion that this paper has nothing to offer for a physical journal, and if at all, it should be rejected and sent to the Journal of Mathematical Physics. Indeed, the paper contains a review of some mathematically trivial material on spinors. I told you it was trivial. It's high school stuff. He's right. I assume it's a he. Maybe I should say they. And with all sort of play with them, yes, you saw me play with them, didn't you? It's all true. And after a long number of occupied pages, not to come to any physical result, conclusion, or even implication. Obviously, they couldn't be bothered to make it their way to the end of the paper where all the predictions were summarized, but never mind. Whoa, kind of a kick in the stomach. Have you ever had a referee's report like this? There's something wrong with the physics community when this is the kind of report that you can get back. If you're a graduate student, do not write a report like this. Notice how it is entirely opinionated, entirely non-specific, and leaves the author with absolutely no clue what to do, except maybe try it at another journal. Don't do that. Referees' reports should be made public so that we can see what kind of things we say to each other. Like I say, it kind of put me back. What do I do now? What I actually did, this is some advice from Sean Carroll. I started looking at things like, are you a crank? You know, Andrew, are you a crank? And this was one of the best lists that I found. And Sean Carroll, very sweetly, he gave me a list of, these are the things that you should do. If you're a crank and you want to kind of up your game, this is what you do. Number 1, acquire basic competency in whatever field of science your discovery belongs to. Okay. I'm good with that one. I do actually clear that particular bar. Number 2, understand and make a good faith to confront the fundamental objections to your claims within established science. Probably the most mysterious thing to me is, how come Wilczek pointed out this spin 10 thing in 1998? He's a smart guy, I heard. Yes. How come he didn't notice each one's a wild spinner, so you need 1 extra bit, so it's got to be 6 bits if you're going to use? Why did he not notice that? Why didn't Georgi notice that? Why didn't Greshov notice that? Why didn't Weinberg, for goodness sakes? All these. So I must be wrong, right? there can only be one conclusion, that Andrew is wrong. And I've tried to think, what is it that could have gone wrong? One is that you're not taught about spinors in high school, which you should be. So, and again, if you teach quantum field theory, you should teach it in this fashion. It's much easier than the other way of teaching it. So maybe that's a problem. The second thing is the Coleman-Mandula theorem that says you can't do this. The Coleman-Mandula theorem says if there are non-trivial analytic scattering amplitudes, as appears to be the case in standard quantum field theory, then the space-time and internal algebras must combine as a direct product. Ergo, take a grand unified theory like spin 10, it must be the product with a space-time group, which is spin 3-1 plus translations, and they must combine as a direct product. Well, does spin 11-1 escape that? Well, of course it does, because spin 11-1 has 12 dimensions, and the internal dimensions are the space-time dimensions. So, tick. But what about the other one? The Coleman-Mandula theorem actually says that if you have an internal symmetry group and a space-time group, they must combine as a direct product, but only the symmetries that are actually there. Any broken symmetry doesn't have to be a direct product. And the standard model algebra and the Dirac algebras are commuting subalgebras of the spin 11-1 algebra. And that is all that you need to satisfy the Coleman-Mandula. It's quite a restriction, requiring that the Dirac and any unbroken symmetry commute. It's a restriction. I've said the idea was obvious, and I think it is obvious, but it's not so obvious to carry through that puzzle. You can see that somehow the puzzle needs to be assembled, but exactly how to do that isn't obvious. It took me a while. The third advice that Sean gives is present your discovery in a way that is complete, transparent, and unambiguous, so that other people can use it. Please, other people, use it. Yes, come on board. Show me it's wrong or something. Under that category, he says, if it's a physics theory, let's face it, it's going to involve math. In this day and age, nobody is going to be moved by a model of elementary particles that comes expressed as a set of three-dimensional sculptures constructed from pipe cleaners. Guilty as charged, right? I am definitely a crank according to these criteria. Okay, but let's try and follow some of this advice and make some predictions. Evidently, spin 11-1 is not the world we live in today. We live in the standard model, or actually a broken version of the standard model, and space-time. So how do you break down spin 11-1 to the standard model? Well, it turns out it's quite a restriction, because when you break space, when you break the number of dimensions from however many it is to 4, then you must satisfy the Coleman-Mandula requirement that the Dirac algebra and whatever other algebra that you have, they must commute. They must be commuting subalgebras of this overall spin 11-1 algebra. And that's a tight constraint. And it turns out that there's only one minimal symmetry breaking chain. By minimal, I mean if you don't add any other ingredients apart from spin 11, this is what you're forced to have. It goes from spin 11-1 to spin 10-1 for reasons which I'm not going to go into. That's a restructuring of space-time that happens before grand symmetry breaking. Then there's grand symmetry breaking of spin 10-1 to what's called the Patti-Salam group, which is spin 4 cross spin 6, multiplied by the Lorentz group. And then at 10 to the 12 GeV, this breaks down to the standard model, which then breaks down to the current world at about 100 GeV. The top line is the prediction, the bottom line is the standard model. In the standard model, it's Higgs fields that do symmetry breaking. And you can ask, is there a structure of Higgs fields that does this? And the answer is yes. And it turns out, again, there's only one choice. And that choice turns out to be a 66 component bivector, which means it flips 2 bits, Higgs multiplet. One of the rules of Higgs fields is that the original Higgs field has to be a multiplet of the unbroken symmetry. So it has to be a multiplet of spin 11.1. Now, the gauge bosons, the carriers of the forces, the W's and the Z's and the gluons, they are in the bivector or adjoint representation. And this is the unique solution for the scalar component, the Higgs component. It is also in the adjoint representation, or in other words, the Higgs sector is just a match of the gauge sector. It's a scalar spin 0 versus the gauge sector, which is spin 1. And in particular, I've written down what 2 interesting fields. Part of the symmetry breaking process is one component of the Higgs field acquires a non-zero expectation value. It rolls down the hill. You start at the top of the hill, and then it acquires a non-zero expectation value. And then other gauge bosons acquire masses and eat up, as people say, the other gauge bosons. The grand Higgs field is this one. You can see this color pseudoscalar comes from that adjustment. That's the clever trick. Any minus vector. But it's a product of the 2 t vectors. Doesn't exist in spin 10, but there it is. That's the thing. It carries 1 unit of t charge. That's why I call it t. And it serves to flip the t bit of the right-handed neutrino. There's the right-handed neutrino. There's its left-handed anti-neutrino partner. It's called a Majorana mass, and it's only the right-handed neutrino that can acquire a Majorana mass because all other fermions have standard model charges which have to be conserved, and it's only the right-handed neutrino that has no standard model charge to conserve, so it can have its bit flipped. So it requires a Majorana mass of about 10 to the 12 GeV, which is this number right there. The electroweak Higgs field is this one. Again, there's a color pseudoscalar in there, and then the time bit kind of goes away when you put in a mass term because there's another gamma t in there, and you're left with a y. So the Higgs field carries 1 unit of y. Yes? The electroweak Higgs field. It's built into this whole system. I don't have to pull it out of thin air. All of the Higgs fields come from the same thing. If you compare this to the symmetry breaking scale system in spin 10, spin 10 for one doesn't have a unique symmetry breaking. It can go either by SU5 or spin 4 cross spin 6, and there's a few other options. But it also requires at least 3 Higgs sectors. First of all, it requires a bivector sector, which flips 2 bits to break ground symmetry. Then it requires something that flips 1 bit to do electroweak symmetry breaking. And then it requires to get a Majorana mass for the right-handed neutrino, which later produces a small mass for the left-handed neutrino by the seesaw mechanism. You need a 126 component pentavector which flips 5 bits. More predictions. You can figure out from the running of the coupling parameters, this is something that is well known to quantum field theory people, you can find out where forces unify. So spin 11.1 predicts an intermediate symmetry breaking to spin 4 cross spin 6, which is the Patti-Salam group proposed as a grand unified theory in 1974, at 10 to the 12 GeV. So there's this combination of coupling parameters which should be 1. And here's the running of the coupling parameters from low energies. This is electroweak scale. And at 10 to the 12, that's where they get this combination is equal to 1, and that's where you get that. So that's 10 to the 12. Grand unification. At grand unification, you've got the Patti-Salam thing gets rid of one of the bits, and you're left with just the weak one and the color one, and they unify at 10 to the 15. Below this is SU3, and then above it's spin 6. So unification is predicted at 10 to the 15. What did I do after that phys rev referee, which was like a gut punch? I went to the APS April meeting and I gave a talk, and I thought maybe someone can come along to me and say, Andrew, you're talking balderdash, or B, Andrew, this was invented a long time ago, or C, Andrew, you've made an error. Sadly, none of that happens. But a few months later, in September, I received this email. Dear Professor Hamilton, I am the publisher of Classical and Quantum Gravity. I saw you give a talk at the April meeting. It's well matched to our journal. I'd personally like to invite you to submit a paper to us. Now, if you're a professor, some of us are, you get emails like this every day. Maybe graduate students also get lots of emails like this saying, we have very much admired your work on nanobot brain surgery and would invite you to be a plenary invited speaker in our... So I ignored the one in September, but I got a repeat saying, did you get our email? We're really serious in November. And I thought, maybe I should respond. So I submitted a paper in January. Now with Tyler. Where are you, Tyler? There you are, Tyler. Tyler is a graduate student who works with me on this kind of stuff, and he is just wonderful in providing me advice on what to do, because I have no diplomatic skills. Tyler has all those skills that I completely lack. Anyway, here it is. The authors work out the possible unification of the four fundamental interactions, blah, blah, blah. Although the adaptation of the internal symmetries residing in standard model is done in detail, and the correspondences fit well in some sense, the gravitational sector in no way shows itself in its most natural form, blah, 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 blah. The authors have enough experience and talent for reaching this target. Oh, thank you for complimenting me. But it doesn't stop them from saying it's more appropriate for the authors to send this paper to a journal related to high energy physics. They very politely said, would you like us to transfer it? It's a cognate journal, so I said, sure, go ahead. So a week later, it took 3.5 months for the referee to get. So a week later, early May, Tyler and I submitted the revised version of this paper, and 4.5 months later, we get a report back. Here's what it says. My reasons for rejecting this manuscript are, it adds minimal new results, and it's written in an unclear fashion. Thanks for being specific. Okay, here's some specific things. It's very difficult to parse which components of the manuscript are truly original. Well, the bits where I refer to other people are not original, and the bits where I don't refer to other people are original. Okay, but my bad. You have to tell a reader and a referee, especially when you're saying something that seems, this can't possibly be right. Yes, this was my idea and nobody else had it before, as far as I can see at any rate. Because otherwise, you can't do this. You're not Ed Witten or somebody. If it was Ed Witten, well, that would be a different thing, wouldn't it? And then, more stuff. How does this resolve the current problems of detecting new particles at LHC? And you say, oh, there's an entire industry on doing that. I don't know how many people there are working on the Large Hadron Collider, but I can read lots and lots of papers, and I promise I've read lots and lots of papers, coming up with a little widget that makes a little change that might be observed in the Large Hadron Collider or the next upgrade of it. Fine. That's not where I came from. I came from, can I figure out physics that I can use inside black holes? I was going to say I don't care about the Large Hadron Collider. I do, because it's wonderful. It's testing things. And it did find something. It found the Higgs boson. This manuscript could have been written 20 years ago. Absolutely true. It should have been written by Wilczek 20 years ago, back in 1998. And probably it should be written back in 1970s. Georgi or Glashow or Weinberg, all of them should have done this. Why didn't they do it? I have no idea. It should have been done. It's obvious. Despite being correct. Oh, thank you again. Once again, my mathematics apparently hit the bar. The authors have not demonstrated how it advances our knowledge of particle physics. Bottom line, please submit to another journal. So that's where it is. It's currently sitting with Physica Scripta, and I hope it's less than 3 or 4 months this time round. I'm almost done. The penultimate section of the paper is called predictions, the one that comes after just before the conclusions, and there's a whole bunch of them. This is a condensed version of the one in the paper. So there's a bunch of predictions. Don't tell me there aren't. 1, spin 11, 1, like spin 10, predicts a right-handed neutrino. 2, spin 11, admits a unique minimal symmetry breaking chain. Number 3, SU5 cannot be on the path to grand unification because its generators fail to commute with the Dirac generators, and so on and so forth. Down to 9. Number 9 is something that could conceivably be tested. The Paddy-Salam group predicts 8 gauge vector bosons beyond those of the standard model, comprising 2 right-handed weak gauge bosons and 6 leptoquark gauge bosons with a ratio of masses 1.1. Unfortunately, it's a prediction up at 10 to the 12 GeV, which is just a little bit more energetic than the most energetic cosmic rays observed. So right now it's out of reach, but it's a prediction. What can I say? Number 11, the only evident candidate for cosmological dark matter is an ultralight scalar with vanishing standard model charges, the scalar counterpart of either the photon or the Z boson. And remember I told you the Higgs sector, the scalar sector, is basically a match of the vector sector. So for each gauge thing, there is a scalar. If it's to be dark matter, it has to be stable, and that means one of 2 things. Either there has to be a symmetry, a conserved quantity that prevents it from decaying, or else it has to be light enough that its decay time exceeds the age of the universe. That last one, an ultralight scalar, is actually quite popular in the astrophysical literature at the moment. And then the second half of that predictions thing is called places to pick holes. And I quote from a famous paper by Coleman and Weinberg, introducing the Coleman-Weinberg mechanism. We are very much aware that we are exploring unconventional ideas, that there may be some basic flaw in the whole approach which we have been too stupid to see. Yes, I totally agree with that. Let me go down to the bottom place to predict holes. It's possible that spin 11.1 is already ruled out by proton decay. The predicted energy scale is 10 to the 15 GeV, which is less than the lower limit of 4 times 10 to the 15 GeV, inferred for spin 10 models by King et al. 2021 for the super Kamiokande upper limit on the proton lifetime. However, that's spin 10, which is different from spin 11.1. So the calculation actually needs to be done. And please, people, yes, you can. If you're one of the people who does those kind of things, my calculation was simple. It was 1 loop and then an abrupt transition at the Paddy-Salam. You should do it properly and see whether you get, oh, this is ruled out. We can move on. Last slide. The complicated DNA of earthly life is a language written with 4 letters, T, A, C, and G. It may be, as Lenny Susskind has proposed, that the complicated DNA of the universe is encoded in the labyrinthal convolutions of the folded up dimensions and the stringy fields that coil them. If spin 11.1 is correct, then the letters of the DNA of our universe are the 6 bits T, Y, Z, R, G, and B. Thank you.
Thank you, Andrew. We have time for questions. It's high school stuff. There's got to be lots of questions. Yeah.
Have you discussed the matter with Soren Postprep?
Nope. You could.
Pass the microphone. All right. Other questions?
Chris,
It's not really a question, but
go ahead with the microphone.
it's not a question, but I saw that you passed one of the tests for not being a crank.
What's that?
I never saw anything written in all caps.
TACG.
Other questions?
So just simply, what is the complication by adding the additional quarks which exist?
What is the complication?
To the spin 11.1 if you add the additional quarks? 'Cause there's certainly more than up
Oh,
and
you
down.
mean the three generations?
Yes.
Yes, this only does one generation. The three generations have to be something different. There's three generations of fermions, but only one generation of bosons. So whatever those generations are, it's different from the thing that produces the bosons. My favorite idea is the same one as the string theorist model, which is the number of generations is dependent on the geometry of the hidden internal dimensions. That would be my best guess.
Other
Mike.
questions? Andrew?
Yeah, thank you. I seem to remember something like the standard model of particle physics is valid in flat space-time, but not otherwise. Is that correct?
Standard quantum field theory kind of works in Minkowski space-time, and you can put in curved space-time and do calculations at the one loop level, as Tyler is currently doing inside black holes at the moment. But the problem is, if you go beyond one loop, it becomes increasingly unrenormalizable, so it's not clear what goes on. So you have to do something different. My guess is string theory may be on the right track, but yes, that's what it is. Quantum field theory is really Minkowski space.
Yeah. Yeah.
Maybe just some general remark concerning the problems you addressed with publishing. I've read a while ago, actually a couple of years ago, but not too long ago, that had there been a review system like nowadays, when Einstein and Heisenberg and Schrödinger published their papers, probably none of them would have been published because they were way too speculative. So I think the remarks you made there are really pretty important, and and they address a problem right now, and it's in various directions. I think. I mean, one, that a clear paper like yours, or I mean, by the way, just for those who don't know me, I'm a mathematical physicist. So I think the mathematics you described here about the spin 11.1 algebra is very beautiful, and it's clear, and I think that's a good thing to be published. And somehow, on the other hand, I have the impression that somehow in some parts of theoretical physics or math physics, it's more important to be overly complicated, even confusing. So actually, I find it almost as a compliment that one referee wrote and complained that you did not include the M and F theories. Actually, I'm glad that you didn't, yeah, because that would have been, I mean, from my point of view, yeah, please, would have, I think this made things more obscure than they are. And then another comment is, I mean, your predecessor talk is on the Rocky Mountain, I mean, as you know, but maybe not everybody here in the lecture hall, is on the Rocky Mountain Math Physics Seminar YouTube channel, and it's one of the one with the highest clicks, the highest numbers of views, and you are roughly on the same level like Barry Simons, a big star in math physics. So it's your work is acknowledged, I would say, but maybe not in the in the somewhat flawed standard reviewing system as we have it now. Yeah.
Thank you, Marcus, for your kind comments. I do accept some blame. I should do better anticipating what referees are going to say. In our latest version, Centre Physica Scripta, we added about 50 references to the recent literature, most of them to the Large Hadron Collider, just to prove that then we're not completely stupid. It has to be said that the Large Hadron Collider really places no constraint, or at least the non-observation is completely consistent with our predictions. I think I will stop, and I think we've kind of hit 1:15, so thank you very much, everybody.
Okay. Thanks, Andrew.